All right. Good evening, everyone. So we will start for today. Um, we will continue our discussion from the previous class regarding the quasi-Richo method. This method is for a collocated grid, as I was telling before, and it also takes care of pressure velocity splitting problem. So before going into the course, have any questions, Jose? Like regarding the assignments or like week 7, apart from your doubts, do you have any other questions regarding assignments?
Yes, sir. In assignment of week 7, I have actually one question. It's like I want just give me a minute. I will show you that question. Okay.
Sure. Assignment of week 7, right?
Yes, sir. Week 7. Sir,
Uh-huh.
there was a question. That question number 3, saying about order of the decomposed matrices in Lu decomposition for a given order n by n. There is a question like that. So
Right. So actually, this is week 7's assignment. You haven't submitted it yet. So I won't be able to give you the answer, but maybe I can give you some thoughts. Okay. So
yes, sir.
you understood what is LU decomposition, right?
Yes, sir.
Basically, you have a matrix, and you are decomposing into L and U. Is it?
Yes, sir.
You have a matrix A. Let's say it would be a square matrix. Let's say n cross n, something like that. So what you are going to do is, your system of equation to solve is Ax equal to b. Okay,
Yes,
right?
sir.
Now you have to invert this matrix A inverse b. So if you invert this coefficient matrix, then you are going to get the solution x. So but finding this inverse is how we are going to solve it, right?
Yes, sir. Okay. So means like order of this matrix only we have to find.
Right. So here we have we need the x is the column vector, and a is the coefficient matrix. This using how you are going to solve this is, you have to invert it to the other side. So there are various methods. One of the method is LU method. So what you are going to do is, you are going to change this A into L times U. Okay. So L is a lower triangular matrix, U is a upper triangular matrix. Okay. A is the order n cross n, that's what they have given. Okay. And they were asked to find you what is L and U's order. So you should find it. For that you need to understand how LU decomposition is done, right? So they are going to replace A with L and U. So your system of equation is Ax equal to b, right? So you substitute Lu in terms of instead of A, you will have Lu x equal to B, right? So this is a lower triangular matrix, this is upper triangular matrix. Now what you can do is you can replace Ux as a D, okay, some other matrix, and you can substitute it back here. Then what happens? LD is equal to B, okay, and then
Yes.
you find the D. So D would L inverse B, or you know it is a lower triangular matrix, right? So it's going to have elements only here. So you can simply do forward substitution, right? You can do forward substitution to this to find D. Once you find D, you have Ux equal to D. So substitute this D here. So ultimately you need to find X. Substitute the D here. Now this is a upper triangular matrix. It's going to have elements only in the upper triangle, right? And here there is going to be X, and this D you just now found using a lower triangle. Using forward substitution you found the D vector actually. Now you can do backward substitution. So from backward you can go to the forward to find the X values. For finding all this you need to find L and U, and that's what it is discussed in the lecture. So you were asked to find order of L and U, am I right? So order of decomposed matrix. So these two
Yes,
matrices,
yes.
yeah, so this matrix you need to find. So I can't give you the answers because it is not yet it's not yet submitted, right? When is the deadline? In 3 days.
Sir, actually 14th February.
September.
Sorry, 14th,
Right.
14th, 14th, 14th September, sorry.
Right. So you were supposed to find this L and U. Okay. So basically from here itself you can get. I will not give you the answer. You need to find it. So
Yes, sir, I understood.
A is a matrix. L and U is also the same matrix, right? So to find the order. Any other doubts? Is there?
No, sir, thank you.
Uh,
Understood now.
okay. So Renju Raj, do you have any doubts regarding assignments or lectures, so that we can go ahead with the.
No, sir, I'm yet to solve that assignment.
Okay, so previous assignment solutions, do you have any other doubts?
No, sir, no.
Okay, okay. So if there are no more doubts, I will continue with today's discussion. Today we are going to see quasi-Richo method. We actually going to continue where we left in the last class. So if you remember in the last class, this quasi-Richo method, we were trying to. So this is a kind of another method. So in lectures you would have studied simple R, simple C methods, right? So those are for staggered grids. Um, so please feel free to stop me in between if you have doubts. So all those techniques are for staggered grids, and some techniques are there for collocated grids also. But you well know that collocated grids are having pressure velocity splitting. Okay, so but there are few methods which overcome this uh, problem of pressure velocity splitting. As you know that collocated grids, we are storing the we are storing the property values at the cell center, and the algorithm is also going to be very easy to implement. That's why people always prefer collocated grids. But because of pressure velocity splitting, um, people have to use staggered grid. But this method, quasi-Richo method, and few more methods, Richo method, and all those methods, they overcome this problem so that you can implement collocated grid itself to get a solution, right? So that's why we will see this. So in your week 8, if you check your videos, lecture videos, so week 8 would be to implement all these whatever we taught in a test case, which is a lid driven cavity flow. Lid driven cavity flow is actually a test case for testing lot of algorithms, right? So if you are developing a new algorithm, let's say like simple R, if you are developing a new algorithm, if you are coming up with a new algorithm for solving Navier-Stokes equation, what people usually do is they will first apply it to this test case called the driven cavity flow, and they will check whether the solutions you obtain is correct or not. So that's how you will validate your program or algorithm. Okay, so that's why it is a very basic case, and you are encouraged to do that. So in your week 8, you are supposed to solve that lid driven cavity flow using programming. Okay, if you have gone through week 8 lectures, would have already showed you the programs, and one thing about that program is it's for staggered grid, and they are going to implement simple algorithm, right? So uh, it, yeah, it's for a staggered grid. So what we will try to do here is, this method is for a collocated grid, and in your free time you can implement this method also, and you can arrive at the same result. So I'm just giving you the advantages of using this method, and you can, of course, you can use it for collocated grid, right? So in last class, what we did was we stopped in between because of time constraints. So, but what we found was we found how we are getting pressure velocity split, right? So maybe I will go through once again from first. So as I said, this is for collocated grids. Uh, the what we have to solve is, we have to solve continuity and momentum equations. So we have a continuity equation. This is the discretized continuity equation. Since it's a finite volume method, we have a control volume here. So as per the continuity equation, the flux going out minus flux in equal to 0 for a incompressible flow, right? So that is what written here. If you see u times delta y, so u I plus half delta y, which is going out, minus u I minus half into delta y, which is coming in. Okay, this is in x direction, and in y direction v j plus half is going out, minus v j plus half is coming in. Okay, so it's just del dot v equal to 0, or in a integral term it's going to be u dot n ds equal to 0, our continuity equation, and the discretized form is written as a star equation, right? um, and we have our cell of interest is P, and it has east, west, south and north. The delta x and delta y is cell dimensions. Okay, and now we have momentum equation. So the momentum equation is going to have some convection term. The convection term is the inertia term. We have that non-linear terms, right? The non-linear terms goes into convection term, and there are diffusion terms, the viscous diffusion u times del square u. So this goes here, viscous diffusion, viscous uh, yeah diffusion. So this convection and diffusion term is there here, and here we have the transient term, right? So we have this dou u by dou t, right? Rho times dou u by dou t plus the convection term is equal to diffusion term plus pressure gradient, right? So the transient term is here, and we have a convection term, we have diffusion term, and we have a pressure gradient term. So similarly we have y momentum equation. So this equation is again for a finite volume method. So for a finite volume method, if you discretize for this control volume, you will end up getting this kind of equation. Now our aim is to find velocities and pressure, right? So you need to find u at n plus 1, v at n plus 1, and pressure at n plus 1. N plus 1 is the, let me write it down, n is previous time step, plus 1 is present time step. So our aim is to find u at n plus 1, v at n plus 1 and t at n plus 1. So but we have two equations, I mean three equations, two momentum and one continuity for a 2D flow. If you have a 3D flow, you are going to have three momentum and one continuity. Four equations you are going to have. Similarly, you have to add w of n plus w at n plus 1 also. So you have four equations, three equations and three unknown. But these are highly non-linear systems, so there is some method to solve this coupled equations, right? So the first step, as you all know, in a simple algorithm also, what you do in first step is you will predict some velocity and you will predict the pressure, and based on predicted pressure and the predicted velocity you will correct the velocity. So for all the so if you take any incompressible solver, this is a solution algorithm or solver, let's say, um, it is going to predict the velocity and predict the pressure, and based on predicted velocity and pressure it's going to correct the velocity. So if you take simple happen. Say simple or simple C, it has few modifications like addition of pressure term in a prediction of velocity. So few more steps is going to involve, and then they will make it a separate solution algorithm. So any basic solver or solution algorithm is going to predict velocity and pressure, and then they are going to correct it. So this is called segregated approach. In a coupled approach, what we will do is we don't do it in steps. We will do it at a stretch. Maybe we will have a slight discussion on that by the end, the coupled approach. So in in this segregated approach, in the quasi-Riccio method, first step is to again predict the velocity. Okay, so what we will do is we will take the same equation, we will use the same equation to predict it, and but we will not consider pressure gradient term. Okay, so if you don't consider pressure gradient term, see these are evaluated at nth time step, we already know these are, and this is also evaluated at n time step. This is not n plus 1 because we are predicting it, so it becomes cap, right? So that's how we will end up with this equation number 2. You see rho delta x delta y, u cap, u the convection diffusion, no pressure gradient, right? So there is no pressure gradient. Without knowing the pressure gradient, we are just predicting some velocity. Now you have predicted some velocity, but do you think it will satisfy continuity equation? Basically every velocity field should satisfy continuity equation, right? So uh, it will satisfy continuity equation, whether it satisfies continuity equations or not. There Raj.
Sir, it will satisfy the continuity equation because
So you are telling it will satisfy?
yes, sir.
So okay, why do you say it will satisfy?
Sir, because in the continuity equation also we have only velocity part only, and this equation is also without pressure. Means like it can satisfy
Right.
the equation.
So yeah, so now here you need to understand one thing. So what we used is we used momentum equation, right? We didn't use the star equation yet, right? So whatever the predicted velocity, it satisfies the momentum equation without pressure gradient, right? But we didn't use continuity equation itself. How it will satisfy continuity equation? Actually it won't satisfy continuity equation. So why means it has velocity, continuity equation doesn't have pressure, but doesn't mean that equation is same as momentum equation, right? Continuity equation is mass conservation, and it doesn't have pressure gradient, of course, but this star equation and this one equation is not same, right? So if something you are finding from one equation, this doesn't tell you that it satisfies star equation just because some term is missing. Okay, so whatever you predicted the velocity, it won't satisfy continuity equation. So mathematically, if you see, it won't satisfy continuity equation. But physically, if you think, if there a flow is happening and there is a velocity field, okay, so what drives that flow? There should be some driving force, right, to for a flow to sustain. Let's say a flow through a pipe, okay. So from one pipe, one end to next end, if the flow has to go, what will what drives the flow?
There should be difference in energy.
Right. So energy or pressure difference, right? So
Yeah.
this pressure difference is going to drive the force, and you have predicted some velocity which doesn't have pressure difference or pressure gradient. So if it doesn't have pressure gradient, how it will satisfy continuity equation? So the predicted velocity won't satisfy continuity equation. So whatever we found till now is just a predicted velocity just dropping the pressure gradient term, and it won't satisfy continuity equation. But finally your corrected velocity, right, that u n plus 1 p n plus 1, everything should satisfy the continuity equation. Because basically mass has to be conserved. Mass cannot suddenly jump into the flow, right? It cannot gain or it cannot lose. Whatever mass comes in should go out, right? So the predicted velocity won't satisfy continuity equation, but the corrected velocity will satisfy continuity equation. So we will come to that later. So that's how it there will be so that is actually a link to our step 2. So now we need to predict the pressure. Okay, so before predicting the pressure, what we will do is we will find uh, the velocity u n plus 1 in terms of predicted velocity. Okay, so what we actually going to do is you taking the first equation, and then you are subtracting with the predicted velocity, this 2 equation. So when you subtract it, what happens? Un drops out, right? This is minus, and this is also is there. So these things drops out. This u1 will drop out, un term, and this convection term will drop out because you are subtracting these 2 equations, right? Term will drop out. So if you subtract these 2 equations, you will end up getting this kind of equation where u at n plus 1 is the corrected velocity, which is predicted velocity minus delta t by rho times the pressure gradient, which is at n plus 1. So actually it is coming from this equation. So this part is dropped, this rho delta t is going that side. So that's how you end up getting this third equation. So finally now you have to find at n plus 1 time steps velocity using the predicted velocity and the pressure gradient. But still we don't know the pressure gradient. If we know the pressure gradient, we can find u at n plus 1, right? So now we need to find the pressure gradient. That is our step 2. Step 2 is to find the pressure gradient. Now how are we going to find the pressure gradient? Now if you go through these equations, we have 3 equations, momentum and continuity, right? Now we used momentum to get the velocity, predicted velocity. Now continuity is still remaining. You didn't use the continuity, and you know that this n plus 1 will satisfy continuity equation. So what we will do is we will use continuity equation to obtain the pressure gradient. So process of doing that, we will end up getting pressure Poisson equation. Okay, so we will see that now. So once we find dp by dx here in equation 3, we get u1 and v1. But how we will find dp by dx is using continuity equation, because we already used momentum equation for a predicted velocity. one more equation which is remaining is continuity equation. But you see, continuity equation doesn't have pressure gradient. How will you find pressure gradient using continuity equation, right? So we will look into the continuity equation more closely. Okay, so if you look at the continuity equation, u at I plus half j and u at I minus half j at n plus 1, everything is at present time stuff which we don't know. Similarly, j plus half and j minus half we need to know. So you need to find these four quantities so that you can use the continuity equation. So how we will find is, the easiest way to think about is, so continuity needs this four velocities, right? So once you find the velocities, you can put in the continuity equation and you can satisfy the continuity equation. Now how are we going to find this? So this is at I plus half, right? So if you look at the let's draw it here itself. This is our control volume, and this is I comma j, this is I minus half comma j, this is I plus half comma j, this is I j minus half, j plus half, this is j plus half, right? So the continuity equation needs velocities in these phase centers, right? If we are in a staggered grid, we are storing velocities at the phase center, so you can easily take it. But now we are doing it in a collocated grid. So how we will find this center values? So what usually easy way, we have I comma j, here we have some velocity. Similarly, we will have so this is one control volume, this is one control volume, this is I plus R, right? This is I, this is I plus 1. So you need to find velocity at this point. So what people usually do is, people means everyone's instinct is, so I have velocity here, I have velocity here, so I will just do interpolation. So in between I have some velocities, I will just do interpolation. So what you will do is, you will take that half times u of I and u I plus 1 j. Okay, so when you do this, what we found in the last class was, when you do this, which is linear interpolation, we end up getting pressure velocity split. That is what we found in the last class. So how do we get that? So we found this, okay, and u I comma j at n plus 1 is actually the predicted velocity, and here we have pressure gradient. So when you substitute these things here and then substitute this whole thing in the continuity equation, and then if you simplify it, the pressure gradient term, if you discretize the pressure gradient term too, you will end up getting pressure velocity split. So that is what we saw in the last class. So if you continue doing this, okay, you will end up getting pressure velocity split. When I say pressure velocity split, what I mean is, if you have a grid like this, right? Now you are finding the velocity here by using the pressures here and somewhere outside, okay, instead of adjacent nodes. Pi plus 2, this is Pi, this is Pi minus 2, right? So you are finding velocity here using this and this pressure instead of this and this pressure, right? So because the cell is constructed here, you need to and the flux is going in and out here, you need to use these pressures, three pressures. But while following our instinct of linear interpolation and substituting it in the continuity equation, we end up getting split like the pressure field and velocity field is getting split. It is not getting coupled because the pressure here is it should drive the velocity, but pressure somewhere else is driving the velocity, which is not desired, right? So that's why people went for staggered grid, but few scientists, um, they were able to come up with an workaround such that this pressure velocity split doesn't happen. So this is where the intelligence of few people comes into play. So what they did was, I have a equation, uh, new time steps equation in terms of predicted velocity and pressure gradient. I need to find facial velocities, right? So instead of using that time steps velocity, they used the predicted velocity and pressure gradient to do that. So they actually used, for to find this, they actually use equation number 3. So we'll see that how. So if you see u of I plus half j, so here we have u ij at n plus 1, which is predicted velocity times pressure gradient at ij, right? So similar thing, this u of I plus half comma j is actually predicted velocity at I plus half and then pressure gradient at I plus half. Now we have one more problem. Now you don't know u cap at I plus half, right? So because you stored the predicted velocity at the cell centers only, you didn't find the predicted velocity at the faces, right? So for this they did interpolation. Okay, instead of doing the interpolation for the un plus 1, they did interpolation for predicted velocity. Okay, and then uh, they they simply discretize this. So you can see that I plus half, right? So if you draw the stencil here, so this is I, and this is I plus half, this is I plus 1, and I minus 1, this is I minus half, right? So from here to here the distance is delta x, right? So if you do let's say central differencing to this pressure gradient, okay, this pressure gradient you are doing central differencing, what will happen? You need to find the pressure here, pressure gradient here, and you are using central difference, right? So it will be pi plus 1 minus pi divided by 2 times delta x by 2. This is delta x by 2, right? Times delta x by 2 becomes delta x. So now we have a equation for facial velocities at n plus 1, right? Similarly you can write this for I minus half, that is you wrote it for I plus half. Now you write it for I minus half v j minus half v j plus half. Okay, so if you do all this, if you find all this, okay, you find all this and substitute in the star equation, which is the star equation. Star equation is nothing but the continuity equation, right? So in this continuity equation, if you substitute these kind of equations into the continuity equation, what you finally end up is this big equation. So if you look at this equation carefully, this is predicted velocity at I plus half, this is also predicted velocity at I minus half divided by 2 delta x, right? And this is delta times pi plus 1 ij I minus 1 and I comma j plus 1 j minus 1. You see, now you are finding the pressure. Now your pressure gradient is not I minus 2 or I plus 2 anymore. It is a pressure gradient having I plus 1 and I minus 1, right? So you actually overcome the pressure velocity split by simply using the equation you derived from the predicted velocity, right? So so how does this look? Can you guys guess? So let me draw the stencil here again. um, this is I, this is I plus 1, this is I minus to this is delta x, right? So can you tell me about this equation? So it's actually u I plus half minus I minus half divided by 2 times delta x, right? So what is this approximation? So this equation comes from which approximation?
Central difference.
Right. So this term is actually central differencing for which one? Which property? This comes from central differencing, but which property you are doing central differencing? For predicted velocity, right? So this term, can you can write it like delta times u by delta x, right? Can you write it like this? Right? This term you can write it like this, right? Because dou u cap by dou x is actually, if you do central differencing, you are going to end up in this approximation, right? So I'm just simply writing it. So do you guys agree this?
Yes, sir.
So if so, this is actually central differencing for velocity, predicted velocity. You see, we have a cap. So similarly, we have a central differencing for predicted velocity in the y direction. Now you have p I plus 1 I minus 1 times delta x square term. So can you guys guess this part? What is this approximation? It's taking pressure at this value and addition of pressure at this value and minus 2 times pressure at this value. So where do you get this? Going to be approximation for second order gradient, right? Central difference second order gradient, second order derivative, right? So we have a second order central difference second order derivative. So we have a second order derivative of p and we have a second order derivative of p in terms of x and derivative with respect to y also. So what we can do is we can simply rewrite this as, so I'm just instead of, so we are just interpreting this equation. Anyway, we will implement this equation only into our solver, okay? But we will just interpret in some way such that well, how it makes sense, okay? So here we have first derivative of velocity at u direction and first derivative of velocity at v direction, and you have del t by rho, and you have del square p by del x square and del square p by del y square. Here I am using del because I am just interpreting, like I am just simply writing the discretized equation, okay? I'm so if we rewrite this as like this, del square p by del x square, del square p by del y square times p rho times, I'm just rho by delta t, I'm just taking on the other side to get this equation 5. So you see this equation 5 is actually called the pressure Poisson equation. So we are getting pressure from the predicted velocity and satisfying continuity. So the pressure field uh, is calculated based on continuity and the predicted velocity, right? Now if you use this pressure field to find the corrected velocity, your velocity is going to satisfy continuity equation implicitly, right? Because your pressure field has satisfied continuity equation. So if you use pressure field and then correct the velocity, that velocity will satisfy continuity equation. This is how you will ensure the conservation of mass, okay? So that's why this is called pressure Poisson equation, because you have Poisson in terms of Poisson, like this is actually del square p times some function of some function is there. So this is actually kind of Poisson equation. If it is equal to 0, it's going to be Laplace equation, right? So since it's a pressure, it's called pressure Poisson equation. This is a famous pressure Poisson equation which they use to ensure the continuity, uh, uh, conservation of mass of your velocity. Okay, so now if let's again look at this equation carefully. We here we have predicted velocities and we have pressures, right? And you see these are evaluated at n plus 1 time step, which we don't know yet. So, but we don't know only pressure here, but we know the predicted velocity, right? So we can solve for pressure in this equation. So you need to solve for pressure from the pressure Poisson equation. Okay, so that's what we will do in the step 2. So you solve this equation, so fifth equation for pressures. Okay, let me write the n plus 1 also, which is missing here. So this is so this left hand side you don't know anything. Left hand side is unknown, right hand side is known, so you can solve for the unknown pressure. Okay, you can solve this discretized equation for the pressure. So once you find the pressure, this is our step 2. Step 2, our main aim is to find the pressure. Once you find the pressure, you have this velocity, you have this field, right? At first itself we found this. Once you find the pressure, I will put that pressure in the pressure gradient and I will find the corrected velocity. So that is our final step 3. Okay, so you have ui n plus 1 predicted velocity plus the pressure here is what we found in the step 2. So here you will use this pressure to find the corrected velocity. So let me write down it as a, to easily understand. So as a flow chart, if you write, what you will do, first step is to first you need to implement, you need to discretize the domain, right? You need to discretize the domain. So those things comes from the problem perspective. So here you already have everything. So here you need to implement initial condition and boundary condition. Once you know initial condition and boundary conditions, what you will do is the first one is step 1, right? So let's say for time t is equal to delta t. Okay, first one is step 1. Step 1 is to predict velocity u cap and v cap. What you will do, you will use the equation number 2, right? Let's write it simply there. We will use equation number 2 to predict the velocities. Then step 2 is pressure gradient. You need to find the pressure gradient. For that you have equation 5, which is actually del square p by del x square plus del square p by del y square is equal to by delta t, if I am not wrong, and they are going to have del u by del y. Okay, you use this equation to find the pressure. Once you find the pressure, you use equation number 6, correct, velocities. So you will get u at n plus 1 and v at n plus 1. By the way, this would be p at n plus 1, right? So you will get n plus 1 and you will get these two. Now what you will do, you advance the time step and then you again go to step 1. Okay, so for every time step, so once for every time step you need to follow these go through these 3 steps: step 1, step 2 and step 3. Predict the velocity, predict the pressure, correct the velocity. So this is the uh, uh, common algorithm for any solver. Okay, so for quasi-Richo we will solve 2, 5 and 6 equations. So this is 6, 2, 5 and 6 equation. there is something called Richo method, which I will leave it to you to explore it. So why people, because of advantages of collocated method, people actually prefer collocated method than a staggered grid, because it is little bit difficult to implement staggered grid and to get the data values. But collocated you can easily implement in a program and you can easily get the solution. This is just a simple flow. Let's say if you are doing a multi-phase flows, or you are doing more complex physics in which you need to add few more equations also into the system, uh, then it is more easy to use collocated grid than a staggered grid. So that's why people go for collocated grid. And um, uh, before previously the some of commercial codes come with staggered grid, but nowadays since these issues of pressure velocity coupling can be overcome by various methods, people are actually preferring the collocated grid, which is easy to implement. Most of the commercial codes have been converted to collocated grid, I believe. Yeah. Uh, do this either Richo interpolation or few more advanced algorithms have been came. So they use this interpolation. Usually they will find the predict the velocity, use the pressure Poisson equation, correct the velocity. So this algorithm they are using for collocated grid nowadays to for incompressible flows, compressible flows also. Now this is called a segregated approach, right? So what is coupled approach? We have two equations, right? Continuity and momentum. And what we did was we used continuity. First we used momentum, predicted, and then used continuity for pressure, and then we corrected it. So this is like step by step method. So what is coupled method? Coupled method, what people will do is instead of this prediction and correction, people directly find u n plus 1, v n plus 1, and p n plus 1 in one go. Okay, because you have three equation and three unknown, you should be able to solve it. Okay, let me give you an example in terms of a compressible flow. So if you take a compressible flow, the main challenge in compressible flow is you have density. Density is also varying. Okay, so density is varying in a compressible flow. In incompressible flow, we will take density for constant. That's why it comes out as a constant in our equations, right? Here, our density is also varying, and uh, since density is varying, you can't solve with continuity and momentum, right? Because it becomes rho, w, and p. We have five unknowns now. We have five unknowns, but we we have only four equations. Yes, Hussein. Do you have any doubts?
Sir, sorry to interrupt, sir.
Yeah,
Sir,
yeah, no problem.
actually, I wanted to ask that it's like you have said that rho is varying, right? So in the compressible flows, sir, but in the compressible flows we also take that in viscid flow means like we can assume that the viscosity is means we can assume that the flow is in viscid means there is no viscosity like that. So, but in the case of incompressible flow, we have to take the viscous terms also. So means that is the advantage also in this type in the case of compressible. So, what's your point of view, sir, about that?
Right. So in compressible flow, we ignore viscous because inertial terms are dominated by viscous stresses. It is advantageous, but the density is varying, right? So you have four equation and we have five unknown, right? In an incompressible flow, what we have is we have viscous terms. So we have this mu times dou square u by dou x square plus dou square u by dou y square dot 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 something will be there, right? but you see velocities are only varying, viscosity is a constant, right? So but the density is not varying in an incompressible flow. In a way it is advantageous because we are ignoring viscous terms, but for more accurate prediction we have to add anyway the viscous terms, okay, for any flow. Okay, the problem with compressible flow, the major missing term in compressible flow is this density. So this density we haven't seen in incompressible flow. I mean, we have seen, but as a constant we have seen the density, but here the density is varying. And now we have 5 unknown and we have 4 equations, right? So how will you close the equation? You have this uh, ideal gas equation, right? So what is that ideal gas equation? P is equal to rho RT. You have this ideal gas equation, but rho is equal to P by RT. So rho is dependent on pressure, so you can use this equation, but you see we have another temperature is coming in. So till now we haven't used energy equation at all. Energy is where temperature comes in. We haven't used energy equation at all, but suddenly the temperature comes in. So what we need to solve is we need to solve for energy equation too. So in energy equation it will give us temperature. So we can use this temperature and we can use the pressure from momentum equation and we can find the density. Alright. So now we have 6 unknowns: rho, u, v, w, p and t, and we have continuity, 3 momentum, 1 energy, right, and 1 ideal gas or any equation of state. Now we have 4, 5, 6. So we have 6 unknown and 6 uh, equations, right? So now the system is closed, but the complexity has increased far, right? Because you added another partial differential equation which you need to solve now, and all these three are linked. That's why compressible flow is little bit complex to solve than incompressible flow. You do you agree with it?
Yes, sir.
So now we will look into, so what people usually do is, since there is a very tight coupling between these equations, we have momentum and energy is coupled with continuity, and then ideal gas equation, everything is fully coupled here and there because pressure, density, temperature, everything changes suddenly. But still you can do segregated approach. It doesn't mean like you can't do segregated approach, but you can do segregated approach. But people usually prefer for coupled approach, which is uh, may I which is actually more accurate in prediction of compressible flows. So for example, if you take Euler equations, so Euler equation is nothing but Navier-Stokes equation without the viscous terms. You all know, right? So how will you write? It would be dou rho by dou t plus dou by dou x of rho u is equal to 0. This is your continuity equation. Similarly, you will have dou rho u by dou t plus dou by dou x of rho u square, right? Or rho u plus dou by dou, um, how it will be, dou y of rho u v plus dou by dou x of rho u w is equal to 0, right? Similarly you will write for rho v by dou t, and similarly you will write for dou rho w by dou t. So these three are momentum equation, and you finally have energy equation, dou rho e by dou t plus few terms. Yes, Jose?
Sir, actually, I want to ask that is that, sir, as you said that we have to take the ideal gas equation also, right? PV is equal to RT. Yes, sir. Sir, but in that case, it's like when we assume that when we say that density is changing, sir, but its major effect is on pressure. Okay, means like the less effect is of temperature as compared to pressure. Sir, so
I
means
didn't
like
get.
what will be the
The density
sir means
difference
like
is
the density is changing because of pressure, okay, majorly, but temperature effect because of the density change is less.
Uh,
So
okay, so actually, um, for a compressible gas, let's say for a gas, um, because of both temperature and pressure, you will see density difference. So um, uh, it actually depends on both. It is actually coupled with ideal gas equation only. So you can't just so how do you say that it is less dependent on temperature? Because you see, rho is actually directly dependent on pressure and inversely dependent on temperature. So when the temperature increases, rho is going to decrease, right? So this is you can't say this is major and this is less. Okay.
but actually, in some textbook of fluid mechanics, some is that they say that compressibility means that the major the flow the density changing because of pressure, okay, as compared to temperature. So because if we consider also incompressible flow, and we can and when we take see that temperature difference, so it can also change the density in the case of incompressible flows. So that's why I was thinking like that.
So actually that is not true. Uh, for a compressible gas, the density both depends on both pressure and temperature. So you can go back and look into the book. Uh, Maybe they would have told you in a different sense. Maybe for some limiting case, they would have referred you in that way. But actually, density depends on both pressure and temperature. Let's say for a CD nozzle case, uh, the pressure temperature both varies, um, as density also varies. Okay, so, um, so there is no way you can say that it has less dependence on pressure and more dependence on temperature. Okay, maybe you can go back and look into the textbooks again, uh, but this is for sure. Density depends on both pressure and temperature, and it is given by ideal gas equation, right? So um, uh, these are for compressible gases. Let's say for Mach number greater than zero point 0.3. Okay, or uh, so for compressible gases, the density is dependent on both pressure and temperature. I'm not getting any example for this right now. Um, maybe,
Yes, sir.
but it is coupled based on ideal gas equation. Ideal gas equation or any equation of state like van der Waals equation of state. So basically what I was trying to say is, as we have a pressure gradient here also, it is not equal to 0, dou p by dou x, similarly dou p by dou y, but the viscous terms won't come, or we are neglecting it because it's a Euler equation. So what they will do is, in a coupled approach, they make something called some like vector form of equation. Okay, so so yeah, so is equal to some constant h. Okay, so here this q is actually rho, rho u, rho v, rho w, energy e. Okay, similarly we have this flux terms e, f, g and h. So what they will do is, and then finally they will use this vector form of equation and they will discretize it based on whatever the discretization schemes we were seeing now. So central differencing, all these schemes, they will use it to discretize it, and then they will find the q. Once they found the q, what they will do is, q1 is rho and q2 is rho u, right? So they will if you want u, they will write q2 by q1 to get the u back. So similarly they will write all these. So energy is actually internal energy, let's say let's write it as I energy plus half v square, right? Okay. So yeah, sure, Raj. So they will use this relations to uh, find the variable q. So once they found the variable, they will take back the velocities and temperature, pressures and density from this. So that's how they will get the say the coupled that's how they will do the coupled approach. Here there is no prediction and correction. They just uh, use this vector form of equation to find the variables. So this is the coupled approach. You just solve the equation at once. Um, in our segregated approach, whatever we saw is for uh, is it has different steps. In a sequential manner, you are solving three different equations. All right. So by this, I will stop. Um, uh, Come back. So in the next class, what we will do is we will try to uh, use this for lid driven cavity. Okay. So we try to use this approach for a lid driven cavity flow, and we will see how to implement it. All right. So I will stop here.